Hello, Mr. Sorrentino here again, doing another one of my videos for Math 31, section 6.4, matrix operations. We had learned about using matrices to solve systems of equations, and there are other methods we can use matrices to do that. However, they do involve us doing some operations, one of which in particular is multiplication of matrices in order to do that. So we want to learn something about how to perform various operations on matrices before we go much further with this. So the first example, you're given these matrices, and I'm going to do these mostly by example. You're given these matrices here, and you're asked to carry through some addition and subtraction and things that you see below. Now, these first ones involve addition, subtraction, and scalar multiplication. Scalar meaning that I'm multiplying a matrix by a number. More definitive, I'll say a constant. We're going to eventually learn how to multiply two matrices together too, because you can certainly do that. There really is no division of matrices. We do learn how to multiply by inverses. As far as adding two matrices together, given two matrices that have this, they have to have the same dimensions. So that's what this is all saying here. All this mumbo jumbo here is saying that they have to have the same dimensions. Sometimes they call that the order of the matrices as well. But, you know, they have to have the same number of row and number of columns. If they don't, you can't add them or subtract them. And all you would do is just add and subtract the corresponding parts. And the scalar product, if I multiply a matrix times a constant, then every single number in that matrix gets multiplied by that constant. It's not a row operation, it's multiplying by a constant. And they do show some properties over here which, you know, some of them are just kind of go along with the properties you already know so much with them. Addition of matrices is commutative, associative, and things like that. There are matrices, you know, that have identities and inverses. We'll talk about those as we move along the line. So if these are the matrices that we're given, I'm going to zoom out a little bit here, you're asked to perform these operations down here. So A plus E, I'm just going to rewrite the matrices. So as you can see here, they are both 2 by 2 matrices. They have the exact same dimensions, so I can in fact add them. The result was also going to be a 2 by 2 matrix. And all I have to do is add the corresponding parts. So I'm going to add the 3 and the 2 and get 5. The negative 4 plus 1 is going to give me negative 3. The 2 and the 4 is going to give me a 6. And the 1 and the 9 is going to give me a 10. It's a negative 9. I know there was an issue with it. Negative 9, so that should be a negative 8. For addition and subtraction problems, I would say it's not really worth using the calculator for it because of the fact that it's going to take you longer to get it into your calculator and set up than it would be for you just to do the operation. I mean, addition and subtraction should be something that isn't extremely difficult for most of you by now, and the numbers you're going to be dealing with in these matrices under most conditions are going to be relatively small numbers. A minus B means I'd be taking the matrix 3, 2, negative 4, 1, and subtracting the matrix 3, 1, 4, negative 2, negative 2, negative 2. As you can see here, this is again, A is a 2 by 2 matrix. This one here is 3 by 2. 3 rows, 2 columns. 3 by 2. These are not the same dimension. Therefore, this is undefined. You can't do the subtraction. Negative 4 times F, or negative 4F. We might lose sight of those matrices up there, but you should have them on your sheet so you know what they are anyway. So that means I'm going to be doing negative 4 times the matrix 2, 0, 9, negative 1, 2, negative 4. which means every one of those numbers in the matrix gets multiplied by -4. So this is -8, this is 0, -36, 4, -8, +16. 2c minus 3d. Well, as we just mentioned, in C here, 2 times C means I'm going to take matrix C and multiply all the numbers by 2. So I'm just going to do that as my first step. I'm going to rewrite what 2C is. 2C is going to be 4, -2, 10 in the first row, -2, -6, and 20 in the second row. And I want to subtract 3D. So I'm going to go to matrix D and multiply all the numbers by 3. So I'm going to have 3, 3, and 12 in the first row. And I'm going to have 18, -18, and 21 in the second row. Now both of these matrices are 2 by 3. Therefore, I can definitely subtract them. I do have to be careful about how I subtract them though. 4 minus 3 is 1. -2 minus 3 is going to be -5. 10 minus 12 is going to be a -2. -2 minus 18 is -20. -6 minus -18. Minus a negative is going to be plus. So -6 plus 18 is going to be 12. And 20 minus 21 is going to be a -1. And that would be the end of that one. For the last one, 2e plus 3f. Again, we know what e is. 2 times e means I'm just going to take all the numbers in e and multiply it by 2. So I'm just going to do that. Starting off, I'm going to have 4, 8, 2, and -18 plus 3 times f. I'm going to have 6, 0, 27, -3, 6, and -12. I went by columns that time. But as I look at these in more detail now, this is a 2 by 2 matrix. This is a 3 by 2 matrix. They don't have the same dimensions, so this would have no solution. And so those are the operations for addition, subtraction, and scalar multiplication. Now, when I have to multiply 2 matrices together, that becomes a different story, and it becomes a little bit more involved. And I'm going to demonstrate it for you. They give you some verbal description of what it is. So if we look at what your textbook has for matrix multiplication, for an m by n matrix A and an n by p matrix B. So basically they're saying that the second dimension of the first matrix has to be the first dimension of the second matrix. We also sometimes call that inner dimensions. When we look at the two dimensions of the matrices written, left to right, the ones that are closest together in between are the inner dimensions. The outer dimensions would be the ones that are further on the outside. Basically, they're saying here that you would do A of I to 1 to B. It gets to be basically that you're going to be moving along the row of the first matrix and a column of the second matrix. And I'll show you what this looks like whenever we actually do the procedure. That's where some students have issues. It's a totally different procedure that they're used to doing for any other kind of multiplication. So I'm still using the same matrices that we had before. So I'm going to rewrite out the 2 matrices. So these are the 2 matrices, A times E. This is a 2 by 2 matrix. And this is a 2 by 2 matrix. Now they're the same dimensions, but it's not being the same dimensions that makes me able to multiply them. I can multiply them because when I have them written in that way, these inner dimensions are the same. So multiplication can be done because those are the same. The outer dimensions tell us what the final result's going to be. The final result's going to be another 2 by 2 matrix. Here's how I perform the necessary steps. I'm going to move along this row and this column. So what I'm going to have here is I'm going to have the 3 times 2 plus the negative 4 times the 4. For row 1, column 2, I'm now going to go down this column on the second one. So when I do my operations, I'm going to have 3 times 1 plus negative 4 times negative 9. Now I'm ready to do row 2, column 1. So I'm going to do row 2 with column 1. And so I'm going to have 2 times 2. So the first one in the row goes with the topmost in the column, and then you work your way right on the row and down on the column, plus 1 times 4. And then lastly, you're going to do row 2, column 2 to get what goes in row 2, column 2 in the final answer. And then I'm going to have 2 times 1 plus 1 times negative 9. So multiplication actually involves not only multiplying but also adding. And you're not just taking the numbers in their position. I'm not just doing 3 times 2 and getting 6 and saying that's what I'm doing here. That isn't how matrices work. It works that way for addition and subtraction, does not work that way for multiplication. So 3 times 2 is 6 plus a negative 16 is going to give me negative 10. 3 times 1 is 3 plus negative 4 times negative 9, which is 36. 3 plus 36 is 39. 2 times 2 is 4 plus 1 times 4 is another 4. That's going to be 8. And 2 times 1 is 2 plus negative 9 is negative 7. So that's what A times E equals. Now when I look at E times A, a lot of students automatically assume, let's like numbers, that you can reverse the multiplication in a matrix. There are some matrices you can, but under most circumstances, you're not going to find that matrices are commutative. And we'll demonstrate it here. Now again, they're both 2 by 2 matrices. So the inner dimensions match, which means we could do it. The outer dimensions tell us that the answer is going to be a 2 by 2 matrix. And so as I go through this, I'm going to do row 1, column 1 to get what goes in row 1, column 1. So I'm going to have 2 times 3 plus 1 times 2. Now I'm going to do row 1, column 2 to go what gets put there. And I'm going to have 2 times negative 4 plus 1 times 1. Now I'm going to do row 2 of this one and column 1 of this one, and I'm going to get 4 times 3, which would be multiplying these two, plus negative 9 times 2. And then lastly, I'm going to do row 2, column 2, and there I'm going to have 4 times negative 4 plus negative 9 times 1. And so that's what I'd have to perform to make this happen, and that's going to equal, well, 2 times 3 is 6 plus 1 times 2 is 2, so 6 and 2 is 8. 2 times negative 4 is negative 8, plus 1 is going to give me a negative 7. 4 times 3 is 12, plus negative 9 times 2, which is going to give me a negative 18. So 12 plus negative 18 is going to give me a negative 6. And lastly, 4 times negative 4 is negative 16, plus a negative 9 is going to give me a negative 25. So notice that, these two are not equal. So under most circumstances, you're going to find that multiplication is not commutative. So be careful with that, and don't assume that it is. Don't assume if you calculate what A times E is, that you know what E times A is. So, and this procedure works the same way when I have matrices that may have 3 rows or 3 columns or whatever the case may be. So let's try this one. Let me write out what B times C is. So there are those two matrices. Before I even bother to do any multiplication, this is a 3 by 2 matrix. This is a 2 by 3 matrix. So the inner dimensions match. So multiplication can be done. And the final answer is going to be a 3 by 3 matrix. So I have to make sure I'm making room for a 3 by 3 matrix. So as I do this, and again, I'm going to go row, column, row, column. So I'm going to have this row and this column. So I'm going to have 3 times 2 plus negative 2 times negative 1. This row now with this column, I'm going to have 3 times negative 1 plus negative 2 times negative 3. And then I'm going to do this row here now with this column. And it's going to give me 3 times 5 plus negative 2 times 10. That takes care of the first row on the first matrix. Now I'm going to do this row and this column. So I'm going to have 1 times 2 plus negative 2 times negative 1. Now I'm going to do this row and this column. So I'm going to have 1 times negative 1 plus negative 2 times negative 3. And then I'm going to have this row with this column, where I do 4 times 5 plus negative 2 times 10. And now I move on to the last row. So this row and this column, I'm going to have 4 times 2 plus negative 2 times negative 1. This row and this column, I'm going to have 4 times negative 1 plus negative 2 times negative 3. You're seeing a lot of repeats on this because of the fact that I do have a column in the first matrix that's all the same values. That's not going to happen all the time, so keep that in mind. And of course, for this row and this column, I'm going to have 4 times 5. This should be a 1 times 5 up here. 4 times 5 plus negative 2 times 10. So when I work all of these out, I end up getting 8, 3, negative 5, 4, 5, negative 15, 10, 2, and 0. So that's B times C. Really, the only thing that's different with part D is I have the same two matrices but they're in a different order. Now, this is a 2 by 3 matrix. This is a 3 by 2. So the inner dimensions still do match. Cool. So I know I could do the multiplication. Now, though, I'm expecting a 2 by 2 matrix. So when I do this matrix here, I expect to have 2 rows and 2 columns, and that's it. And so when I go through and do this, I'm going to have this row with first this column. So I'm going to have 2 times 3 plus negative 1 times 1 plus 5 times 4. And then when I do this row with this column, I'm going to have 2 times negative 2 plus negative 1 times negative 2 plus 5 times negative 2. I'm now going to do this row with this column. So I'm going to have negative 1 times 3 plus negative 3 times 1 plus 10 times 4. And then when I do this row with this column, I'm going to do negative 1 times negative 2 plus negative 3 times negative 2 plus 10 times negative 2. And when I work all those out, following my order of operations and all, I end up getting that this is 25, negative 12, 34, negative 12. So as you can see, that not only are they not commutative, sometimes the results are matrices that are even different sizes. So if they're different sizes, there's no way they could possibly be equal to each other. So remember, you got to take it in the order that it's actually coming by. And so if I look at these two matrices and I rewrite them, now this is a 2 by 2 matrix. This is a 3 by 2 matrix. These inner dimensions do not match. So that means that this, in fact, has no solution. You cannot multiply those two together. If you had been asked to do F times E, where you had the 3 by 2 coming first and the 2 by 2 coming second, that would have worked, because the inner dimensions would have matched. So this one you can't do. F times E you can do, which is another case, which is another indicator that there's no way that these matrix multiplications are commutative. And so that's how you do the matrix multiplication. Now, example 3, I'm going to show you how you can use your calculator to do some of these matrix operations. I'm going to focus on multiplication primarily, and how you can get your matrices set up on your calculator and perform the operations and so forth. So let's have a look at example 3. Now here in example 3, this one's nice and tells you exactly what kind of matrices to set up and whatnot. Whereas some other problems you might be given along the way don't. And as I go through this, I'm going to explain why what they're telling you to do is really the only way you could possibly do it. You have this information here which tells you you have 4 bakery items: white cake, bread, coffee cake, and sugar cookies, and the flour, milk, eggs, and butter needed to make each. So they want to see this is what how much they use by weight for the various items. The unit cost for each ingredient is 15 cents for flour, per whatever unit of measurement they're using for this, 28 cents for milk, 54 cents for eggs, and 83 cents for butter. So they're saying, okay, well, write this, what we have in this table is a 4 by 4 matrix that we're going to call M. That's pretty straightforward because, now, one of the things I have to consider along the way is if I make M a certain way, it's going to usually affect how I'm going to make any other matrix that might have to be working with this. So M, now for the sake of our discussion, I'm going to also keep in mind what these various things represent. This is the white cake, this is the bread, this is the coffee cake, and this is the sugar cookies. And this was for flour, milk, eggs, and butter. They tell us how much it costs for each unit of this stuff, and they want you to make a cost matrix C, but they do tell you it's a row matrix, which means it's only one row. So C, based off of this, is going to be 0.15, 0.28, 0.54, and 0.83. But again, I have to remember what these are. This is, how much it costs for flour, how much this costs for milk, how much this costs for the eggs, and this how much it costs for the butter. And of course, what I have here is dollar amounts. They tell you to find the product C times M. So they come out and tell you, they're saying and this is going to be what we call, D. They say for part D here, it should say part C. So the result matrix would be the result of that multiplication. Well, first of all, when I look at this, now, the reason why they're saying to multiply by C times M, if I do C times M, now C is a 1 by 4 matrix, and this is a 4 by 4 matrix. So if I do a 1 by 4 and a 4 by 4, I could do that multiplication, and I would expect that D would be a 1 by 4 matrix. If I had chosen to represent this as a column matrix instead, so say I let C be a column matrix, they didn't give me any direction. There are a few problems where they don't really give you any direction. And this would be my F, M, E, and B. 0.15, 0.28, 0.54, 0.83. Now, first off, this being a 4 by 1 matrix, I couldn't do C times M. So C times M would be no solution. I'd have to do M times C. The problem is, what do I get out of each circumstance? One of the things that we mentioned before is, if I had M, I'm going to say M times C1, just to keep this straightforward. This being a 4 by 4 and this being a 4 by 1, I can multiply it in that order just fine. But I have to also think about what would be the result I would get as well, which is why sometimes I had to make the decision whether it's a row matrix or a column matrix. Here they told us they were nice about it. If I'm doing C times M, C being the row matrix, again, I know I'm going to get a 1 by 4 matrix. And I know that because I'm keeping basically the row heading of the first matrix C and the column headings of the second matrix M. Knowing this lets me answer the question right away of what it is that, for part D, what does the resulting matrix represent? Because what I have here is I have the bakery items, the white cake, the bread, the coffee cake, the sugar cookies, and I have the dollar amount. So basically it's going to be the cost of producing each item. I don't know what those amounts are yet, but that is what I'm going to get from this. If I had tried to do it the other way using a column matrix and did M times C1, again, I have a 4 by 4 matrix, a 4 by 1. The interdimensions work so I could get an answer. My final answer would also be a 4 by 1 matrix. But what would I have? Again, I would have the row headings of the first matrix. I would have the F, M, E, and B. I'd have the column heading of the second matrix. This seems to say that, I'm going to have a cost for flour, a cost for the milk, the cost for the eggs, the cost for the butter. What this would basically tell me is, when I produce these items, how much money in total am I spending for each of these ingredients? It's not going to tell me how much I'm creating for each item. So as a result, what I get from each matrix could be a little bit different. And so for this, if I had chosen to do a column matrix, I wouldn't be able to figure how much it costs for each bakery item. I could tell you how much I spent in total for each ingredient. I could say I spent a total of X amount of dollars for flour, X amount of dollars for milk, so forth and so on. And so that's, one of the things you have to always be considerate about, like what you're looking for, because sometimes they'll tell you what you're looking for. Find a matrix that represents the cost of each item. We have to figure out, well, what kind of matrix do I need to set up that goes along with M, and when I multiply it to M, in what order, how am I going to get what I need there? So, that can be a little bit tricky if they don't give you some of the information. Typically, you're not going to be asked to, set up a matrix from a table. You'll have a system of equations you have to set up, and then it's a little bit more straightforward about what you do. So don't be too concerned about picking whether it should be a row matrix or a column matrix and so forth. So I know the cost of producing each item. Now I need to go back and figure out what the product of C times M actually is. And so now it comes time to use the calculator for this, because it does help streamline things a bit. So let's pull out the calculator here. And let me quit out of this, clear this out. I want to be able to multiply two matrices. And I'm going to try to make sure I can see both of them as best as I can. Move that over here. I want to have a matrix M and I want to have a matrix C. And I want to do C times M. So I'm going to let A, because I could do matrix C, but this doesn't get, if I come here to hit second in matrix, under names, these are all the names I could give my matrices. It only lets you go down to J. So you really only have 10 matrix names you could give it. Okay, so I can't find a letter M. So I'm going to let matrix M be matrix A. And so I'm going to say I want to come here and I want to edit this matrix. Matrix M is a 4 by 4 matrix. 4 by 4. And all I have to do at this point is just type in the numbers that I have in there. So I'm just copying, I'm just typing all the numbers in, hitting enter each time, and it just moves along the matrix so I can fill it all in. So this is my matrix M, it's under matrix A. If I come back to second in matrix again, I can see now I have a matrix that's 4 by 4 stored in A. I'm going to go to edit, and I'm going to go to matrix B. I'm going to let that be C. And C was a 1 by 4 matrix. So 0.15. Again, I'm just going to copy what I have there. So going through the menus and doing all this typing takes its time. So you can see why in instances of multiplication, it's best to use it, because it'll give me an answer right away and I don't have to go through the multiplication process. But for addition and subtraction, once you realize you can actually do it, just add the subsequent numbers together or subtract them. It makes it a lot easier. So now I'm back here. I want to do a calculation. I want to do C times M, or in our case it's going to be B times A. So now I'm going to come to matrix. I'm going to choose matrix B. So when I'm under names, it's just going to pull matrix B into my normal calculator menu, times second matrix A, and I get my answer. So going to my answer for C times M now, I'm going to be able to put in what I have up here. That's going to be 0.97, 0.65, 0.8675, and 1.175. And again, recognizing the fact that based up here, this is going to be my dollar amount. This is going to be the white cake, the bread, the coffee cake, and the sugar cookies. And so now I can provide a little bit more detail to part D. I know it's the cost of reducing each item, and so that's going to be 97 cents for white cake, 65 cents for bread. Approximately, so I have to round a little bit on this one, 87 cents for the coffee cake, and about $1.18 approximately for the sugar cookies. And so that's what I get from this matrix. As I said, if I had made it a column matrix before and had to do M times C, I would have gotten the costs, the total costs of each ingredient that I used for, the items that I'm selling. It's not really meaningful because I really don't know how many I'm selling. It's like, the total cost for producing one of each item, which wouldn't be very practical. So, basically in this section, they have a couple problems where they have you just write the equation out. Eventually, we're going to manipulate the equation to solve it. It's usually it's a quicker way once you've established something that you need to do to solve it, and we're going to talk about that when we get there. But basically, I want to be able to write this as basically the multiplication of two matrices equaling the right-hand side. I want to be able to write this as matrix A times a matrix we're going to call X equaling a matrix B. A represents the coefficient matrix. X represents the variable matrix. And B is the result matrix. I want to be able to write it into this format. It's not very difficult, mind you. It's very similar to some of the things we did when we were doing augmented matrices, except now we're writing the coefficient matrix as a separate matrix from the result matrix, whereas in having an augmented matrix, we kind of merge them together. And so basically, for this situation here, this would be my A, 3, 2, 4, 4, -5, -1, -2, 6, -4. I took all the coefficients that I had on the left-hand side times my variables. It's usually going to be a column matrix. And if we stop right there, as far as the left-hand side goes, if you would carry through matrix multiplication the way we would do them, I mean, if we would take this first row here and multiply by the column, that's 3 times x plus 4 times y minus 2 times z, which is what we had on the left-hand side in the very first equation. So, this is relying on you knowing your matrix multiplication, and it's going to equal, of course, 10, 15, and 9 on this side. So that's the answer for this. Now, what eventually we're going to be doing with this is we want to be able to turn this into an equation where we just have x equaling something, and that's going to tell us what the variables are. So it's going to mean if I have x equaling x, y, and z, and I have matrices with a matrix over here with numbers in there, that means that x has to be whatever this number is here. Y has to be whatever this number would be here. Z would have to be whatever this number is here. And if I was looking at this equation, say, well, that's pretty easy to solve for x. I could just say that, x equals b divided by a. There is no such thing as a matrix division. So that's out. And so we would have to say, okay, well, maybe doing the inverse of the matrix times b. Now, we haven't talked about inverses of matrices, but that's what we're going to be moving towards in the next lesson. 6.5 Inverses of Matrices. Before we get into talking about inverses of matrices, let's talk about what an identity matrix is. And an identity matrix is any matrix that if I multiply a matrix to it, in any order, you're going to get back that other matrix every time. But identity matrices are square matrices. So they're square matrices, so 2 by 2, 3 by 3, 4 by 4, etc. And you're going to see this diagonal of ones, much like, basically you're seeing this reduced row echelon form in them. So basically, if I multiply these to a matrix, I should get back the original matrix. Now, any matrix is going to have an identity. There's always going to be at least one matrix, there's going to be an identity matrix that I can multiply it to. It just depends on what order I choose to multiply it in which matrix I would use. So, for instance, considering these matrices down here, A, B, C, and we're going to look at these matrices throughout this this little lesson here. We want to figure out what's going to happen with B times I times B, and E times I, and we want to determine what the identity matrix is. So, I mean, in all these cases, it looks like it's being multiplied by an identity matrix, but these identity matrices may not be the same thing for each time. For instance, when I look at B times I, now B, as I can see up here, is a 3 by 2 matrix. That means if I do a 3 by 2 matrix here, in order for me to be able to multiply any matrix to it, has to have two rows in it, so the inner dimensions work out. So the only identity matrix I could use would be a 2 by 2. And in this case, the final answer would be B. So basically, if I take B times I of 2 by 2, that will equal B. Now, if I do I times B, again, I have a 3 by 2 matrix in B. In order for the inner dimensions to match up, this would have to have 3 columns. So it has to be a 3 by 3 identity matrix. And again, that would equal B in the long run. So in this case, I would have this. Once again, this demonstrates the fact that matrix multiplication is not commutative, because in each case here, I had to have different dimensions in order to be multiplied to B, in order to achieve the fact that I would have, B show up as the product as well. And lastly, down here, E is a 2 by 2 matrix. That means that I has to be a 2 by 2 matrix as well. And that's going to equal E. So I would say that E times I. Now, in some cases, they'll say what the identity matrix is for these. And other times they'll just write I. It really doesn't matter, because we don't usually do a whole lot of instances where we need to multiply a matrix by its identity anyway. In most cases, we're looking to multiply a matrix by the inverse of another matrix, especially when we start doing that to help solve systems of equations. But the whole idea behind an inverse, an identity matrix, is that it helps us define what an inverse matrix is. So let's take a look at that. So the inverse of a matrix for an n by n matrix. So first off, I know that matrices can only have inverses if they're square matrices. They have to have the same number of rows as columns. The inverse matrix, if it exists, now the existence of it first depends on the dimensions of the original, but there's other instances too that we'll talk about, one of which actually involves a topic we'll look at in the next lesson. I'll bring it up here just briefly anyway. That if I multiply a matrix by its inverse, I should get an identity matrix. That's the whole premise behind it. So that's the definition of it. Now, the procedure of finding the inverse of a matrix is what we're going to be looking at doing here. But the whole idea is, it's quite a bit of a longer process to do it. So, if you know ahead of time that there's no way it's going to have an inverse, it'd be best for you not to even try it. So it's just like, okay, I'm not going to bother with this because it's not going to work. So before we're going to determine here if it's at all possible. So for instance, B is not a square matrix. It has 3 rows and 2 columns. So this is not going to have an existing inverse. There's another one here that doesn't have an existing inverse either, and that's this one. It's a square matrix, yes. And it's something that if you started the procedure I'm about to show, to find the inverse of the matrix, you would get to a point where you're not going to be able to achieve what it is you want to achieve. And as a result, I mean, you would just be, have to say that there's no inverse for it. But you would have done a lot of work just to come up to that point. And the fact of the matter is, if there's no inverse for it, you can usually tell pretty quickly. So it has to do with this row of zeros down here. If I have a row or column of zeros only, then it's not going to have an inverse. And that's because this has a determinant. And we're not going to talk about more about the determinant later in another lesson of 0. If a square matrix has a determinant of 0, then it doesn't have an inverse either. So those kind of instances I should be able to tell right away. And with all honesty, if I had a chance to, if we discussed the determinant before this, I would definitely find the determinant of A and the determinant of D before I would start trying to go through the process. Because even if it doesn't have a row of zeros or a column of zeros, it could still have a determinant of 0. Because that's just the way the numbers happen to work out when you calculate the determinant. But that's a longer process, and that's what the next lesson is about. So we're not going to get into that part today in this lesson. We're just going to, I'm just going to let you know that A and D both do have inverses, so I'm going to show the procedure for doing that. So in the case of matrix A, which I've rewritten here just to give myself enough room, the first thing I'm going to do in order to find the inverse is I'm going to augment this matrix with an appropriate identity matrix. So this is a 2 by 2 matrix. The appropriate identity matrix would be a 2 by 2 as well. So when I augment those together, it's going to look like this. And what the procedure is now is I'm going to now use row operations as I had done before to solve systems of equations. But now what I'm going to do this, as I change each row, I'm going to make this left-hand side into reduced row echelon form. And then what's going to happen is this will be changed to the inverse. So the numbers will change, those ones and zeros over there will change accordingly to become the inverses, the numbers that go into the inverse, or the elements that go into the inverse. So what I first do is I'm going to say, okay, well, obviously I want to make this 5 here a 1. So I'm going to take row 1 and divide by 5, or multiply it by a fifth. And so when I do that, my matrix is going to become, now this row down here I've done nothing to. Everything up here gets divided by 5, so this is going to... Now I want to make this 4 down here into 0. So in order to do that, I'm going to take row 2 and subtract away 4 times row 1. So row 1 is going to be unaffected. 4 minus 4 times 1 is going to give me a 0 here. 5 minus 4 times 1.2, well, 1.2 times 4 is 4.8. 5 minus 4.8 is going to give me a 0.2 here. 0 minus 4 times 0.2 is going to give me a negative 0.8 here. And 1 minus 4 times 0 is going to give me a 1 down here still. So I got my first column established. Next I want to get this number here to be a 1. So 0.2 is the same thing as 1/5. So to make that a 1, I should multiply that term and therefore the entire row by 5. So my next operation is going to be 5 times row 2, which means row 1 is being left alone again. 0 times 5 is 0. 0.2 times 5 is 1. Negative 0.8 times 5 is a negative 4. And 1 times 5 is still going to give me a 5. So last row 1 and subtract away 1.2 times row 2. So this row is unaffected. 1 minus 1.2 times 0 is going to give me a 1. 1.2 minus 1.2 times 1 is going to give me a 0 here. 0.2 minus 1.2 times negative 4. Well, 1.2 times negative 4 is negative 4.8. So I have 0.2 minus a negative 4.8, which is the same thing as 0.2 plus 4.8. So that's going to give me a 5. And lastly, 0 minus 5, or 1.2 times 5 is going to give me a negative 6. So those are the numbers I have there. And as I said before, what's now on this side here is the inverse. So I can now say that the inverse of matrix A is 5, negative 4, negative 6, 5. So that's how you find the inverse using row operations. Let's do the same thing for D. So here's matrix D. To find the inverse of this matrix, again, I'm going to start with an augmented matrix. So on the left, again, I have the elements that are in matrix D. On the right, I have the 3 by 3 identity matrix, or reduced row echelon form. And what I'm going to do is carry through the row operations necessary, and so that eventually the left-hand side is going to become the reduced row echelon form, and then the right, the values will have changed until I have what I have for the matrix, so, or the inverse matrix. So I already have a 1 in the top left corner, so I've already established the 1 I want up in the left-hand corner, so I don't have to do anything with that. So what I want to do now is I want to get this negative 2 and this negative 3 to be zeros. So the row operations I'm going to do to accomplish that is that I'm going to take row 2 and add 2 times row 1. And I want to take row 3 and add 3 times row 1. So the only thing that's unaffected with this is row 1. So we're going to rewrite that. So for row 2, I start with negative 2 plus 2 times 1 is going to give me the 0 I was shooting for here. 11 plus 2 times negative 5, that's going to be 11 plus negative 10, which is going to give me a 1. 3 plus 2 times negative 1 is going to give me a 1 here. 0 plus 2 times 1 is going to give me a 2 here. 1 plus 2 times 0 is going to give me a 1 here. And 0 plus 2 times 0 is still 0. For row 3, negative 3 plus 3 times 1 is going to give me the 0 here. 15 plus 3 times negative 5 is going to be 15 plus negative 15. That's going to give me a 0 down there. Negative 4 plus 3 times negative 1 is going to give me 4 plus negative 3, which is a 1 here. 0 plus 3 times 1 is going to give me a 3 here. 0 plus 3 times 0 is going to give me 0. And 1 plus 3 times 0 is going to give me a 1 here. So I got my column of zeros, ones and zeros on the left. And also, the way this happened to work out, I got a 1 in the second column where I wanted to have it as well. And I also have a 0 in the second column where I wanted to have it as well. It's always going to work out nicely for you, but sometimes you might have a matrix that does that. So the first column's already been established. The second column, in the process of going through this, is just as extra baggage. I got the 1 and 0 I want for the second column. Really, the only thing I need to do is I need to change this negative 5 to a 0, then my second column is taken care of. So I'm going to take row 1 and I'm going to add 5 times row 2. And since I'm only changing row 1, the other two rows are going to be left unaffected. So now for row 1, I'm going to do 1 plus 5 times row 2, which is a 0. So 1 plus 5 times, that's going to keep me with the 1 here. Negative 5 plus 5 times 1 is going to give me the 0 here. Negative 1 plus 5 times 1 is going to give me negative 1 plus 5, which is going to give me a 4 here. 1 plus 5 times 2 is going to give me an 11 here. 0 plus 5 times 1 is going to give me a 5 here. And 0 plus 5 times 0 is going to give me 0. So I'm at this point, and I have two of my columns established, and I also have the one down here that I already want. So, I'm already, well on my way for this one. So the last row operations I have to do would be to turn this number and this number into zeros. So to do that, I'm going to go with row 1. I'm going to subtract 4 times row 3. And to row 2, I'm just going to subtract row 3. So the last row is unaffected. For row 1, 1 minus 4 times 0 is still going to give me a 1. 0 minus 4 times 0 is still going to give me a 0. 4 minus 4 times 1 is going to give me the 0 I want here. 11 minus 4 times 3, that's 11 minus 12, that's going to be a negative 1. 5 minus 4 times 0 is still going to be 5. 0 minus 4 times 1 is going to give me a negative 4. Now I'm on to the second row. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. So I got my reduced row echelon form. 2 minus 3 is negative 1. 1 minus 0 is 1. 0 minus 1 is negative 1. Now this is a side note, just so that you're aware of this. A lot of times when you're dealing, especially with 3x3 matrices, you're going to start seeing a lot of fractions when you do some of these divisions. I mean, it just happened to be that this was set up to have a lot of ones and zeros come about doing multiple operations. So, but we got to the end. The left-hand side now has our reduced row echelon form, so that means the right-hand side would be the inverse. So D negative 1, or the inverse of D, would be. And so that's the procedure for doing it. It gets to be longer and more involved. In your note, you're given, how to put this into your calculator in order to find the inverse. And essentially, you put your matrices in, and then if you just do just hit that and just do the x negative 1 key, which is the key right underneath your math button. It's on the far left-hand column. You have your second button, alpha, math, and then x negative 1. That's how you get that little negative 1 there. And it'll give you the inverse of the matrix. So, and as you can see here for B, it didn't work. We discussed why it's not a square matrix. It just didn't work. You notice it says invalid dimensions. So it's kind of telling you that you don't have a matrix that has the right dimensions to have it. Whereas you look at matrix C, when they try to do it here, it says singular matrix. And singular matrix is basically saying that you would get that row of zeros or column of zeros if you were doing row operations. And that's what the determinant actually does also tell you as well. Finding the inverse of a matrix, and if you have a shortcut for doing it, which you can see now you do, you can use your calculator, except on the final, that basically that gives you a shortcut for solving a system of equations as well. So taking point here that I want to solve this system of equations. What they first ask you to do is write the equation in the format A times X equals B. They're asking you to write a matrix equation. The A matrix is the coefficient matrix. B is the result matrix. And they're also defining a variable X here. That's going to be the variable matrix. And so when I write an equation like this, I'm going to take A times the matrix X, which is going to have all my variables. Another reason why you have to make sure you have them all lined up, because now if I multiply these two together, I should get back the exact same thing. 3 times X minus 4 times Y plus 2 times Z, and so forth and so on. And that's going to equal my result matrix. So again, this is my matrix A, this is my matrix X, this is my matrix B. Much like algebra, these are matrices. If I was solving an algebra equation, I would normally say, okay, if I was solving for X, the variable, or in this case the variable matrix, I would usually divide both sides by A. But again, we really don't have matrix division. We do have, however, the ability to multiply by an inverse. So instead of, thinking of it as a division, what I would need to do, essentially, is I need to multiply this matrix by its inverse. And I got to make sure I do it in the same order here. So ultimately, my inverse matrix, or my variable matrix, is going to be the inverse of A times B. Now, at this point, that means that you have to find the inverse of matrix A, and you can do that using the row operation method I just got done showing you. But at this point, just to simplify and make this video a little shorter, we're going to do it with matrix, just by using the calculator. So, and that's what you're kind of being shown here in this information in your notes. You see, I'm putting the matrix A in, the 3, -4, 2, so forth and so on. Matrix B is in. And then I'm just showing here that in my calculation menu, I'm just doing A inverse times B. And I get 4, -7, 3. So that means whenever I'm doing this, and to kind of write it out, my matrix X, which I'm going to write as matrix X, Y, Z, and I'm going to have, that comes out being 4, -7, 3. So, I mean, if you did it all by hand, you'd have to first find the inverse of that matrix using the row operations, and then carry through the multiplication with the result matrix, and you would end up with this as well. And that basically means that for these two matrices here and here to be equal, their elements have to be equal. So X would have to be 4, Y would have to be -7, Z would have to be 3, and that's your solution. So again, that's another method of using this, using inverses to find the solution to a system of linear equations as well. So, and again, you can do it the long way with finding the inverse yourself and then carrying through the multiplication yourself. You can also do it using the calculator at this point. It's just making sure you set it up correctly. And again, if you're not being told one way or another to do it, you can use this method. Just make sure you show what you're putting into the calculator. You will be required to find the inverse of a matrix somewhere during a quiz and or a test. But, this certainly makes it a lot more simplified once I'm able to separate what matrix A and matrix B are and, make sure I multiply the inverse of A times B. And that brings me to the end of this video. If you have any additional questions, please make sure to bring them up in class or see me during office hours. Until I see you in one of those places or until the next video, I'll see you around. Have a good day.